Morning. Welcome to the fourth day of this exciting workshop. Today we have a team to talk about beyond worst case.
Thanks, Elias. It's actually fitting Elias would introduce me because beyond worst case analysis is actually sort of a modification of an old paper of Elias's with Papadimitriou called Beyond Competitive Analysis. So thanks everyone for showing up early. Thanks to the bootcamp organizers for inviting me to come give a talk on a topic that's been sort of near and dear to my heart for a while now, a circle of ideas I like to call beyond worst case analysis. So in this tutorial, I'll try to shine a spotlight on a lot of what I think are really cool results in this area, in this circle of ideas, many of which actually I think have sort of flown under the radar of the sort of mainstream algorithms community, despite being really nice results. So I'll try to, I think they should be more widely appreciated. And then the other thing I want to kind of highlight is there's a ton of opportunities for further work in this area. So some really concrete open problems about algorithms and computational problems we all already care about that I think are really interesting. So I'll try to highlight those throughout as well. At the outset, I should say this is sort of a 2-hour Reader's Digest version of a class that I've given semi-regularly at Stanford since 2009. The vast majority of what I say today was covered in more detail in the course materials. So there's both a full set of lecture notes and there's a full set of lecture videos up on YouTube. So if any of this you find cool, you might want to check that out at some point in the future. So let me start with a clarification. So sometimes, when I use this phrase beyond worst case analysis, I've had people parse it this way and have asked me, so Tim, what would beyond worst mean exactly here? Like terrible case analysis? Abysmal case analysis? So this is how I want you to parse it. So if you like, think of it as alternatives to worst case analysis. So let me start by just, oh, and by the way, feel free to interrupt with questions at any time. So let me begin by saying, what do I mean by worst case analysis and why would you need some alternatives? Okay, so let's say we've agreed on a computational problem, SAT, TSP, whatever. And suppose we've agreed on a performance measure for an algorithm. Okay, so the first one you learn about as a student is the running time, but maybe it's a heuristic for an NP-hard problem, and I care about the objective function value of the solution returned, or the approximation ratio. Maybe I just care about correctness, whatever. So let's say there's some performance measure you want to, say, minimize the cost of some algorithm A for this problem on some input Z of this problem. And the reason analyzing algorithms is so hard is because pretty much any two algorithms you ever look at are in some sense incomparable. But when you talk about the performance of an algorithm, what do you mean? You really mean, a very rich object. You mean a vector indexed by all possible inputs Z that this algorithm ever might be run on. That's the full performance profile of an algorithm. Take any two algorithms, generally one of them will do better on some of the inputs, and the other will do better on the other inputs. So without further modeling choices, there's no unequivocal way to call one of the two algorithms better than the other. There is a sort of very happy but rare exception of instance optimal algorithms. So this is problems where you actually have a single algorithm which is better than every other algorithm on every other input, at least up to a constant factor. And there are some applications. So the term is from Fagan, Lowton, and Noir. They gave some nice examples in database search. And there's also been some great follow-up work in low-dimensional computational geometry. But these are really the exceptions that prove the rule. So even for problems like sorting, easy to prove there's no instance optimal algorithm, you're really stuck with this issue that any two algorithms are just in some sense incomparable. So how to proceed? Well, almost all work in algorithm analysis proceeds by squashing this big performance profile vector down to a single summary statistic. So to each algorithm you attach a single number. Now of course it's easy to compare different algorithms and talk about optimal algorithms. There are some exceptions, like bijective analysis is a concept which works directly with the performance profiles themselves, which has some really nice applications in the competitive analysis of online algorithms. But for the most part, almost everything in algorithm analysis takes this approach in some way or another. So worst case analysis is really just a modeling choice for what summary statistic you're going to use to summarize this whole performance profile. And as it would suggest, you look at the worst of all of the inputs. So you take the maximum over any input you might run this algorithm on of the performance measure. Now actually, usually, especially for something like running time, this isn't going to be a number. This is going to be a function parameterized, for example, by the input size, or maybe some other parameter. But in general, you're going to be taking the worst overall inputs of a given size of that performance measure for that algorithm. So let's review what we tell our undergrads when we teach algorithms. Why do we do worst case analysis? Well, first, if you have an upper bound, that's kind of utopia. A good worst case upper bound on an algorithm means you do not have to reason at all about the inputs that you need to solve. You need no model of the data. Doesn't matter what it is, just run the algorithm, you're going to do great. And if that seems sort of too strong to hope for, well, then there's this cool thing that actually lots of fundamental computational problems actually admit algorithms with really good worst case running times. In fact, almost everything we teach in undergraduate algorithms has this property. So we can get away with it. And then, of course, as for people in this room who actually prove things about algorithms, of course, it's not lost on us that it tends to be quite a bit easier to prove things about the worst case performance than about some other measure that you might want to use. Okay, so that's the last reason. So, so there's lots of killer applications of worst case analysis, but, you go a little bit beyond the problems that you study in undergraduate algorithms, and you start seeing its weaknesses. It starts kind of, having some epic fails for more general problems. So what I want to do next is just sort of review 3 of those epic fails of worst case analysis, which are then going to motivate some of the other topics we discuss this morning. So let me begin with maybe the most famous failure case of worst case analysis, which concerns linear programming. So optimizing the linear objective function subject to linear constraints. So linear programming was really first generally articulated by Danzig in the 40s, and at that same time, he also proposed an algorithm for solving linear programs, the Simplex method. And this kind of blows my mind, but here we are 70 years later, and variants of the Simplex method are still the dominant paradigm for solving linear programs in practice. There are other really good methods too, but still Simplex is used more than anything else. So why? Why so successful? Well, you just run it on some linear program where you care about the answer, and it's just going to tell you the answer really quickly. What do I mean really quickly? Like a typical thing would be linear in the number of decision variables. That's observed in practice quite a bit. So that was in the 40s. In the 1960s, people started thinking about worst case polynomial running time bounds for algorithms. So it was natural to wonder if there was one for the Simplex method. So it was a significant result by Clay and Mincy in the early 70s that the answer, unfortunately, is no. You actually can contrive particular linear programs that force the Simplex method, with kind of any of the common pivot rules, to run for an exponential number of iterations. So the worst case performance of Simplex, you have to concede, is exponential, just by definition. And this obviously, is a terrible performance prediction for this algorithm in practice. And then sort of to add insult to injury, things now are different. But at least initially when the first provably polynomial time algorithms, worst case, came out, they were just manifestly inferior to the Simplex method for pretty much any linear program you'd want to solve. So in addition to just having a very poor performance prediction for the Simplex method, in effect, if you take worst case analysis at face value, it's giving you just really bad advice about how to solve a linear program. It's advocating the inferior algorithm to the empirically superior algorithm. Okay? So this will motivate our discussion of smooth analysis, which will be one of the topics in part 2 of the tutorial. So next I want to talk about clustering, so a form of unsupervised learning. And I want to leave this kind of undefined, sort of vague for this slide. But you're given a bunch of data points, in Euclidean space or in a metric space, and you want to somehow group the data points coherently, whatever that means. So points that are close to each other typically should be in the same cluster. Points that are far apart you hope would be in different clusters. So, this is too vague to reason about formally. So if you wanted to actually, prove guarantees for clustering algorithms, how would you proceed? Well, a very natural way to do it, and there's been a ton of work on this, is you phrase it as an optimization problem. So you posit an objective function defined over all clusterings, and you look for the best one according to that objective function. You've probably seen many examples of this, the k-means, k-median, k-center, and so on. And sort of a meta theorem is that however you decide to phrase clustering as an optimization problem, it's going to be NP-hard, even usually NP-hard to approximate to within sufficiently good constants. Okay, so it's worst case hard even for small constant approximations. On the other hand, this clearly doesn't stop people from using clustering very successfully in practice. It's very widely used algorithms, even really simple algorithms like say k-means or k-means plus. And they don't always work great, but for most of the instances that people care about, they're happy with the results. They get back clusters which they find meaningful and illuminating. So how can theory sort of reconcile these two facts? The fact that it's worst case hard, but you seem to have meaningful results in practice. Well, so there's a strand of literature, which I'll talk in much more detail about shortly, which can be summarized, I think, nicely with the title of a paper of Daniel E. Lineal and Sachs, which is the thesis, the conjecture that clustering is hard only when it doesn't matter. So what does that mean? So, it's an NP-hard problem, so we know there are hard instances. But, what if the hard instances just look like a bunch of random points in space with no really interesting clustering? Then who cares? We're not trying to cluster random points anyways. We're trying to cluster, proteins or something else that has meaning. So the reason you're running a clustering algorithm is because you expect there actually is a good clustering to be found. So the hope would be that if you make that assumption explicit, you assume there's a meaningful clustering to be found, that implies additional structure on the instance, which can actually be then rigorously leveraged by an algorithm and give you provable guarantees better than the worst case. So we'll see that. So that'll be the first main technical topic we discuss. All right, so the last failure case I want to mention comes from competitive analysis of online algorithms. So we heard a lot about competitive analysis on Tuesday from Nikhil and Adam, and also Sefi. And so this is a problem that, that I think Sefi talked about a bit, online paging. So, and this was the original online algorithm problem proposed by Slater and Tarjan in the mid-'80s. And it's familiar to anyone who's taken an operating systems or computer architecture class, right? So you have a sort of relatively small, relatively fast memory, a cache. It can hold up to, say, K pages. And then a sequence of page requests come in online, that is one by one, okay? And when a page request shows up, if that page is already sitting in your cache, great, you incur no cost. If, however, the requested page is not in the cache, that's a page fault or a cache miss, and you have no choice but to bring in that page into your cache. And if your cache is already full, that means you need to evict something to make room for this new page that you're bringing in. So the algorithmic question in online paging is, which page do you evict on a page fault? Okay. Now, yeah.
We can also consider the worst case capacity under some criteria, like clustering. We can think about if the clustering quality is better than some number, then the worst case capacity is how much? I mean, can we consider? Then it's still a worst case capacity, right? But it's meaningful because you mentioned that for most applications, clustering.
So I guess let me summarize. I mean, you can imagine variants of worst case analysis which add meaning, and actually the next slide will be exactly that kind of example, not in clustering but in online paging. So it's not to say that there aren't ways to modify worst case analysis to increase meaning, but the focus of this tutorial will be on a little bit more radical departures from the worst case world in the spirit of meaningful guarantees. But yeah, we'll see a concrete example of that on the next slide. So for paging, right, so that's what you learn. The other thing you learn in your systems classes is they basically tell you what eviction policy you should use or aspire toward, which is least recently used, or LRU. Okay, so this just says, when you have a page fault, see, which is your most recently unpopular page. Okay, so the page which most recently was requested furthest in the past, evict that. And you're also taught the intuition about why LRU works well in practice, which is so-called locality of reference. So this is the thesis which you can empirically verify, that in typical page request sequences, if a page was just requested recently, it's likely to be requested soon in the future. So in some sense, the future is going to look a lot like the past, at least the recent past. And so that's why it's advocated over other natural eviction policies like first in, first out in the systems class. All right, so could we develop theory which mirrors what practitioners observe about paging in practice? So Slater and Tarjan really founded the field of online algorithms and looked at this. And one early observation that they made in their paper is that if you apply worst case analysis, at least in the most straightforward way, to the online paging problem, it's really an epic fail in a couple senses. So what they show is that consider any deterministic online algorithm that you want, FIFO, LRU, other ones, it doesn't matter. There will exist, and no matter how big your cache size is, there will exist a page request sequence so that your algorithm faults 100% of the time. And moreover, in hindsight, if you look at the optimal thing you should have done, so in this case it's called the furthest in the future algorithm, your page fault rate would have only been 1 over k%. So k might be 1,000 or 10,000. So you got a fault rate of 100%. Well, you could have gotten something less than 1%. So in what ways is this an epic fail? The first is just that, it kind of, you never observe page fault rates anything close to 100% from any of these policies in practice. So somehow, taken at face value, this doesn't make a lot of sense. But also, it fails to differentiate between algorithms which we kind of know are different in practice. It doesn't advocate LRU over FIFO. And actually, maybe we shouldn't be surprised about that, because we're told in systems, why LRU beats FIFO, and it's because of a property of typical data. It's because of locality of reference. So if our model never articulates structure in the data, to mirror locality of reference, why should we expect the theory to separate these two algorithms, actually, if you think about it? Okay, so I'm not going to have time to say too much about online paging in this tutorial, but I do want everyone to know that, more than any other problem I've come across, this is the failure of worst case analysis, which led to the most kind of introspection and soul searching among people who do algorithmic analysis. So there's really a really nice kind of prescient literature from the late 80s and the 90s mostly, about how can you dodge, these worst case bounds for paging. Slater and Tarjan already had some suggestions like resource augmentation, but there's many others as well. So I can't talk much about that literature, but I can't resist at least mentioning sort of one result which I like a lot due to Albers, Favholt, and Giel. So, as advertised, this will still be worst case analysis, but they make two changes which give them really interesting results. The first thing is they focus on the page fault rate, an absolute measure, rather than the competitive ratio. And that's very, if you can prove the page fault rate is low, arguably you're happy no matter what the competitive ratio is. But the second thing, which is the part I want to emphasize, is they parameterize the input in an interesting way. Now again, we're used to thinking about parameterizing the input, if nothing else, by the input size. But Albers et al. Propose a parameterization which is really specific to the problem of online paging. Okay, so it's not a general way to parameterize problems, but it's one which is sort of exactly what you want to get the kind of theorem that they get, to get meaningful results about online paging. So the parameterization is through a function f. Think of this as a concave function. And so we say that it's a page request sequence. So basically, intuitively, linear f's are going to correspond to no locality of reference, and super concave f's are going to correspond to tons of locality of reference. That's the way to think about it. So formally, for any particular size w of a window, consecutive requests, we say that a sequence conforms to the function f if there's at most f of w distinct page requests in any window of length w. Okay, most f of w different requests for different pages in a window of length w. So if f is linear, this imposes no constraint at all. Okay, you can just do anything. But you can think about concave f's, which is closer to what you see in real life page request sequences, like f being square root or f being logarithmic, for example. Okay, and so they're going to have a worst case bound about these paging algorithms parameterized by f. So the more locality of reference, we're looking for better performance. So there's a couple parts to their theorem. The first parts already are very satisfying. Okay, so the first thing that their theorem shows is it shows an optimality result for LRU in a very strong sense, in a sense which is function by function, cache size by cache size. So there's a parameter alpha sub f of k. I'll tell you what that is in a second. But the first high order bit here is that you can prove, on the one hand, for every choice of f and every choice of w, every deterministic algorithm has worst case fault rate at least alpha for that f and w, worst case over sequences that conform to f. Meanwhile, LRU, again, for every choice of f and for every choice of a cache size, has a matching worst case page fault rate. Okay? So that's the first thing, which is really nice. LRU is somehow optimal point-wise across choices of f and the cache size. The second thing is that actually alpha is small enough that these results are meaningful even taken at face value, which is actually pretty rare for sort of worst case approximation results. So I'm not going to give you the exact formula for alpha, but alpha is going to be 100% if f is linear. We already knew that. But if there's some locality of reference, so like if f is the square root function, then alpha is like 1 over the square root of the cache size. Okay, 1 over the square root of the cache size. So if your cache size is 10,000, this is saying your worst case page fault rate is 1%. Okay, which sounds pretty good, actually. If f was logarithmic, it would even be dropping exponentially fast with k. All right? So those are the two first things to notice: an optimality statement for LRU in a strong sense, and just performance bounds which are interpretable at face value. Very cool. The other thing we were sort of complaining about on the last slide was that the theory did not differentiate between LRU and FIFO, or for that matter, any other deterministic paging algorithm, but here you can. Okay, so here there are choices of F and K, actually lots of different choices will work, so that, for example, the FIFO policy will not achieve this best possible page fault rate of alpha F of K. Okay?
Do they know what is the gap?
Yeah, there are some bounds on it, so the gap is not that big. But they argue that actually in practice the gap isn't so big either between LRU and FIFO. So maybe it makes sense that, so they can both prove, they can prove an upper bound on FIFO, which is sort of a small constant bigger than 1 times alpha. Yeah. But again, arguably that's sort of in line with what you see empirically. Okay, so I mentioned this result for 2 reasons. One is, like I said, I mean, I'm a fan of this paging literature. I wanted to tell you at least something about it. But also, before we sort of depart from worst case analysis, a broader point I want to make is that, often you can actually salvage really meaningful results in the worst case analysis framework just with a smart problem-specific parameterization of the input. Now, the algorithms community has tons of parameterized bounds of all different types. So for example, in parameterized algorithms and complexity, which is very hot right now, you get lots of running time bounds, which are parameterized by, for example, the size of an optimal solution. But again, what I'm talking about here is not so much generic ways of parameterizing inputs, but really thinking about, what is it you want to say about the problem and about the algorithms, and then what's the appropriate input parameterization, for that domain. I think this is a great sort of success story of that kind of work. And I think there's room to do more of that in general. Okay, so that's what I wanted to say about worst case analysis. So how well did it do? Well, okay, so to give it grades, to give it a report card, I should sort of say what are the subjects? Like, what do we want to grade it on? So that means, like, okay, why are we doing this algorithm analysis thing in the first place? And there's a bunch of different reasons you might want a rigorous theory of algorithm performance. One thing is really pretty ambitious is you might want to just actually have accurate performance prediction for specific algorithms for specific problems, okay? And so this is a lot of what Kevin will be talking about in the afternoon. And here with worst case analysis, you're basically not trying to do this. Right? So if you have any algorithm with a large amount of variation in performance across inputs, obviously by focusing on the worst case, you're punting on trying to predict on typical instances. It's just not what it's meant to do. Now sometimes, if you have very little variation in running time across instances, like for merge sort, say, or a lot of dynamic programming algorithms, then it's fine. You do get actually meaningful performance predictions. And again, for problems we teach in undergrad algorithms, that often is the case. Now maybe you say, okay, that's overkill. I don't really care about having sort of a literal prediction of how good an algorithm is going to do, but I want to know what algorithm should I use to solve this problem. Give me some advice about what algorithm to use. So that means you want to compare them and ideally identify optimal algorithms. And here I think the grade is sort of mixed. There's problems like the ones we teach in undergrad algorithms where worst case analysis gives you great practical advice about how to solve things. Merge sort, Dijkstra with heaps, etc. But as we've seen in these preceding examples, it starts breaking down and you start getting inaccurate advice about how to solve problems more generally. And then the third thing, which we shouldn't forget, is there's other reasons to have a formal sort of benchmark, a yardstick by which you judge algorithms better or worse. If nothing else, for people who work in algorithms and theoretical computer science, if you posit some yardstick by which smaller numbers are just better, the Pavlovian response of everybody is to just brainstorm like crazy and try to come up with crazy new algorithms that do better than the state of the art. And so worst case analysis clearly has been incredibly successful as sort of a brainstorm organizer. So there's really thousands of new algorithms, which I really think probably would not have been invented if we didn't have this this framework to think about. Some of these algorithms are not practical. That doesn't matter. A lot of the ideas are relevant, and a lot of the algorithms are practical as well. Okay, so I've just basically reviewed the well-known reasons why we don't always want to do worst-case analysis. Obviously, when it's wrong, it's because it's overly pessimistic. You can get bad advice about what algorithm to use. And in the pros, I said a pro of worst-case analysis is that there's no data model. That's true when you have a good upper bound, but when it's not working out, then it actually seems like a con that you don't have a data model in worst-case analysis. Or if you have a data model, it's the Murphy's Law data model. Right? So Murphy's Law says whatever can go wrong will go wrong. And so worst-case analysis as a philosophy is saying, I believe the relevant input is a function of the algorithm that I choose right now. Okay? which maybe there's some cryptographic applications where that makes sense, but in general, it's kind of a paranoid and incoherent way to think about solving problems. Okay, so the point being is, what does it really mean to go beyond worst case analysis? For this tutorial, what it's going to mean is that you need to actually commit. You need to articulate some property of the data. So you need to somehow deem some inputs more relevant than others. Now, there's many ways of doing that, right? So just like in algorithm design, right, there's no silver bullet. There's no one algorithmic idea, which is a panacea for all your algorithmic ills. So there's not going to be an algorithm analysis, one magical notion of data which works well for every problem. But just like in algorithm design, there's a bunch of tools. There's a bunch of things that are starting to work repeatedly, and that's what I want to expose you to for the rest of the tutorial. Okay. So we're through the first half of part 1, roughly. So I told you what worst case analysis is and why we might want to do something different. The next part, I'm going to sort of tell you about some of the theory around making precise this conjecture that clustering is hard only when it doesn't matter. And then I'm going to try to convince you that actually a lot of work in sparse recovery, for example, in compressive sensing, is really technically kind of exactly the same spirit of this work in part 3. So any questions before I move on?
You didn't mention at all randomized algorithms.
For paging, you mean, or for what? Or for anything?
In this framework, I mean. Yeah.
Yes, so the randomized algorithms would just come in the very first slide where you talk about the performance measure. So if it was randomized, you could say the expected cost over the coin flips with the algorithm or whatever. Yeah. So the formalism is fine for, you're right that I'm not sure we'll actually see a single randomized algorithm in this talk, but there's no reason why all of these issues are, they're equally well defined and meaningful for randomized algorithms.
I think, for example, a primality test. It's a success of a randomized algorithm compared, although it's not worst case, but it's with high probability.
I would say it sort of is worst case, right? Because the randomization is only over the internal coin flips. So the way I would talk about randomized primality is I would say here you care about correctness. Right, so on a given instance, you either get it correct or you don't get it correct, and that performance measure is then going to be the probability that you're incorrect, and that's the thing that you want to minimize over all inputs. But it's still, if I gave you 2 different randomized primality algorithms, some of which had a higher error rate on some inputs, and the other one had a higher other rate on other inputs, it's not clear which one to prefer. So the issue, I would argue, is the same. Other questions? Yeah.
Where do you see probabilistic analysis of algorithms?
Yeah, so part 2, right, sorry, I meant to mention that. So all of the rest of the tutorial will be these ideas of how do you articulate, relevance for data. The difference between the 2 parts is in part 1, there will not be any distributions. So we'll be looking at deterministic conditions, which are intended to impose, kind of meaning on the instance. Part 2 will be all about probabilistic models. I'll say very little about sort of standard average case analysis, but I'll say a lot about kind of robust versions of average case analysis. Yeah, so that'll be part 2. Anything else? All right, so clustering is hard only when it doesn't matter. What does that mean? Well, there's actually been at least 5 different proposals of how to define instances that have a meaningful clustering. I don't have time to tell you all 5. Let me tell you briefly about 2 of them, the 2 that have been studied the most. So the first definition, and the one which really kind of, in large part, kicked off the work in this area, was by Balkin, Blum, and Gupta. And they call their notion approximation stability. Okay, so let me so again, what is the point of this? The point of this is to define instances with meaningful clusterings. Then we can ask, is it easier to solve clustering on those instances than in worst case instances? Okay, so we're doing the definition first. What does it mean that you have a meaningful clustering? And this is easiest to understand with a picture. So again, we're thinking about clustering. Imagine you posited some objective function, whatever you care about, say k-median for concreteness. So on the one hand, if you could solve your optimization problem exactly, you would get some optimal clustering of the points. And let's assume that this is the target clustering. This is the meaningful clustering that you want your algorithm to recover. Okay, so we have a bunch of data points. We have 3 different clusters, the red one, the blue one, and the green one. Now, k-median is going to be NP hard, so you're probably going to be running some heuristic, some approximation algorithm for the k-median problem. And here's what you're hoping happens. Okay? You know you might not get the optimal clustering back because it's an NP-hard problem, but you know you're going to get something that has, objective function value close to optimal, within a factor 2 or whatever of the optimal k-median objective function value, and you're really hoping that what that 2 approximate clustering looks like is something like this. Okay? So you've noticed that a couple of the blue points have been stolen by the green cluster, same thing with the red cluster, but these clusterings are very close to each other. You basically discover the same grouping of the points into 3 groups as you did before, okay, modulo a few mistakes. What you're really hoping doesn't happen is something like this, that you run your approximation algorithm. It's a 2 approximation algorithm, so you get a clustering with k-median objective within a factor 2 of the smallest possible, and yet, if you look structurally at the clustering you get back, it is really missing the point. Okay, so it took the blue and the red cluster, made them 1 cluster, and then fractured this green cluster into 2 to make up for it. Okay? So if you're running an approximation algorithm on a clustering instance that has a meaningful clustering, you're hoping to get this, you're hoping you don't get this. So approximation stability just says, let's assume that you only get this. So consider an instance, so there's going to be a parameter alpha. Consider an instance where any alpha approximate clustering with respect to an objective function like k-median, any alpha approximate clustering actually is structurally almost the same as the target clustering. Okay. So really there's a second parameter here, an epsilon, which is how different these 2 things can be, but I'm going to suppress that.
So you assume that the optimal is the function design is such a
good question. That's actually not important. So what you do need to assume is that the target clustering doesn't look too different from the optimal solution. So the assumption is that if you optimize the objective function, you get back a clustering that classifies 1 minus epsilon fraction of the points the same as your target clustering.
You also assume that there's only one optimal solution.
No, so every optimal solution, if you like, should be within, classify 1 minus epsilon the same as the target. So I assume there's only one target.
Okay, well, we don't know the target.
That's right.
So there's no way to, if I look at the input,
yes,
and I have an optimization function,
yes,
how do I know that it fit into this?
You don't. So this is not an efficiently checkable condition. That does not mean this is not interesting results. Okay, so, obviously it's only better if you can efficiently check the condition, but I'm pretty happy if there's some sort of plausibility argument that real world data sets might at least approximately conform to whatever definition you wrote down. Now you're taking it on faith, there's no question, and then ultimately you just have to answer it with were you happy with the clusterings you got back from your algorithm or not? But yeah, so there's neither of these 2 conditions are going to be checkable. Yep.
Then aren't you kind of assuming that the problem is not really hard?
That's exactly the question. Good question. So it's not clear. Okay, and actually it depends a little bit with the problem. Exactly, So it's not obvious whether or not making this assumption, it's not going to make it harder, but it's not clear whether it makes it easier or leaves it the same. Okay. It might. You're absolutely right that it seems like it could make it easier, and that will be the theorem.
To me, intuitively, it feels that you are kind of encoding the assumption, like you're trying to say that clustering is only hard in cases that don't matter, but you're kind of throwing away those cases anyway by making this assumption.
That's right. So I guess it's sort of more like a contrapositive. It's saying whenever clustering matters, it's actually easy. That's the way to think about it. Okay. So this is how we're defining, when clustering matters. And again, there's at least 4 other definitions. It's not to say this is the only reasonable one, but it is a good one.
But then do those 5 instances cover everything?
It's not even clear how to define cover everything. Yeah, and again, you can't expect like a silver bullet. I mean, it's just not going to happen, right? So really, we need a toolbox of definitions and sort of ways of sort of thinking and analyzing about problems so that you can try out. Okay, just like an algorithm design, you need a suite of things to try. Yep.
If you really don't care about, if you really don't care about epsilon fraction of points, why don't you exclude them as outliers?
Sure, if you like. I mean.
But we included them in the objective because we believe that they are all equally important, right? Then now, I don't know, because that was a problem, right? So we kept all points in because we believe that all points are important. Mm-hmm. Then now, and then we were making an assumption that it's okay to some epsilon fraction points are okay to move around. Yes.
I mean, the epsilon here is only making the assumption weaker, right? I mean, so I'm saying, should you think about this? This assumption is basically saying numerical closeness in the objective function value translates to structural closeness. Okay? And the bigger you take epsilon, the weaker that assumption is, right? So the more sort of structural non-closeness I'm permitting. So, you know, it's not, I mean, I wouldn't make the connection necessarily to that epsilon into outliers. It's really just a way of making it a more meaningful condition that's more likely to hold for data sets. Yossi?
On the slide you write stable. What do you mean?
It's a definition. So I mean, it means when you pass to, approximate solutions, so basically think about it this way. We're passing from an optimal solution to an approximately optimal solution, and we want the clustering that you get back to be stable in the sense it changes very little. So that's the sense of the word stability. Right, and so this is not stable, right? So this is, you change a little bit in the objective function value, but actually the clustering changes a lot. Okay, so that's unstable. Good. So there's a lot of nice work on approximation stability. Let me just kind of mention, the main result from that Bulk and Blum-Gupta paper. Again, there's lots of analogous results now for other problems. So they think about k-median, the k-median objective function, and they look at alpha approximation stable instances, where alpha for them can be as small as you want. Okay, so it can be any constant. 1.1, for example, would be a reasonable thing to set alpha to. And then, and again, remember, this is our thesis. Clustering is hard only when it doesn't matter. We're defining when it matters as being alpha approximation stable. And now we want to prove that clustering is easy. And indeed, Balkan and al. Prove that. So they say if you have a k-median instance, which is, for example, 1.1 approximation stable, then in polynomial time, you can recover a clustering of the points which agrees with the target clustering except on a O of epsilon fraction of the points. Okay? And what's really interesting about this is, alpha, I said you can take alpha equal to 1.1. There are not 1.1 approximation algorithms for the k-median objective in the worst case. Okay, so we're sort of below the approximation threshold, and yet it really is true that when you impose this sort of existence of meaningful clusters, actually you're not in a worst case instance, you have extra structure, and this is a proof that you can, in polynomial time, identify and exploit that structure. Yishai.
I don't see the dependency on alpha here somehow, right? Because
yeah.
So I see that
can I just
condition that I have a black box that gives me something which is close to optima up to epsilon. I can take alpha, like here I can take alpha being n or something.
Yeah, I mean, so I was glossing it over the rug. So I said, you can in poly time recover a clustering which misclassifies an O of epsilon fraction of the points, and in that big O is the gap is alpha minus 1. So as you take alpha to 1, the number of misclassified points is going to be blowing up. Yeah. Good.
So I'm wondering if something's a bit circular here. So an alpha approximation stable instance,
yeah.
Is that an instance with respect to metric k-median?
Yes.
So you're kind of saying, like, when it's nice for metric k-median in one sense, it's also nice in another sense?
Yes.
Okay. Do you see why that feels like that might...
Well, so the first sense is, okay, so, I mean, really what this is trying to do is it's trying to translate from the language of approximation algorithms, which talks about how close you get to optimal for an objective function, to the kind of guarantee you want in a clustering setting, which is much more about classification error. And in general, if you just approximately solve some k-median objective, you're not going to have small classification error. You're going to get just a clustering which is very different than what you want. And so this hypothesis is a way to sort of bridge those two worlds. It says, well, let's suppose we actually have an optimization problem which is a good proxy of the structural problem. And now, does that change the complexity of the problem? And it does in a sense.
It feels a little bit like begging the question. Is there a way that this could fail?
Yes. There are other problems for which asserting alpha approximation stability does not change the regime in which you can recover good clusterings.
Can you give an intuition of what that would look like?
Sure. I mean, yeah. So basically, sometimes you can just have an NP hardness reduction where I take a worst case instance and then I output, an instance which sort of the objective function values are preserved of everything, but I also have the alpha approximation stability. So sometimes even hard instances can satisfy alpha approximation stability. And there are examples. K-median is obviously not an example. And there are other examples where you have theorems like this as well. Yossi.
If I have an alpha approximation algorithm for a problem, then automatically it's alpha approximation stable?
No. No, the assumption more comes from suppose it was actually useful to have an alpha approximation algorithm in the sense that it gives you back a clustering with small classification error. That's the assumption. So I'll get to this. An interesting theorem is to understand how these types of alphas compare to these kinds of approximation factors. That'll be one of my open questions. Kamesh.
Algorithm tailored to this assumption, or is it like a natural algorithm?
That's a good question. For this particular result, it is a little bit tailored to it. So, and that's one of the reasons why I'm not going to talk about the proof of this. The thing I will talk a bit about the proof, it's actually just a very general purpose algorithm, and the stability condition is only used in the analysis to prove that it works. So, to get the ball rolling, I think it's totally appropriate to use the assumption. But ultimately, you really want to use the assumption only in the analysis, in my opinion, not in the design. Yep.
So does this sort of framework extend to other NP-hard problems, or is there something very special about clustering?
The definitions or the theorems?
Like just the approach of defining something that's alpha.
I'd say the definition makes sense whenever you have a notion of structural closeness of different feasible solutions. That's really the point, right? So we have tons of numerical objective functions. Depending on the problem, you may or may not have a notion of like the distance between two different solutions. But if you do, then there's an obvious analog of this definition. Now then there's the question of, do you have this positive result? And even within clustering, the answer sort of depends on the problem. So there it's much more back to, for every problem, we need to kind of understand it anew.
Maybe you mentioned this before, but how do you precisely, in the previous slide, how do you precisely define close to almost, cluster almost as in all, so how is that?
Good, so you look at what I'm calling the classification error. So you look at the grouping of points in the target clustering, and then you look at the grouping of points in this clustering, and you see what fraction of points are in a different cluster in the two clusterings. So this is meant to have sort of very small classification error, and this has quite large classification error. Yep.
Let's take max sat.
Yep.
If you define the analogous thing for alpha approximate stable, namely not too many bit values change in if you are approximately the maximum thing.
Okay.
Do we know anything better than for max sat under that assumption?
I'd be surprised if you got anything in max sat. It doesn't feel like the kind of problem where you get mileage out of this. And perhaps backed up by that, I haven't seen any work on it. So, yeah. Yeah, so there's going to be, so again, we're going to see lots of different ways of sort of imposing structure on the inputs, and none of them are going to work on even a majority of the problems that you care about, right? Just like no algorithmic technique works on a majority of the problems that you care about. So, the fact that there are success stories on important problems, I think, is sufficient justification. So we care about k-median, we care about clustering. This is a novel positive result, which I think is worth appreciating. Yeah.
Okay, so here's what a little bit how I understand it. Can you explain why it's wrong? It seems like you're saying, okay, say that I have an approximation algorithm that works, then my approximation algorithm works.
Yeah, so the notion of works is different in the two senses. So the first notion of works means with respect to the numerical objective function, you're close to optimal. The second sense of works is in terms of classification error. With respect to a target clustering, you get most of the points correct. And a priori, there is no relationship, really, between those two objectives. So anytime you can establish a link that doing well for one of those metrics does well in the other, that's automatically interesting, because it's often not true. Yeah.
For other objectives for clustering?
There are results on, I think, k-means and k-means, I think. K-center, I think maybe it doesn't work. Yeah. So it works for k-means, but not for k-center. Okay, so let me talk a little bit about this the other stability notion. So this was proposed by Bilyeu and Lineal in the context of max cut, gamma perturbation stable. So again, let me explain it with a picture, say for max cut. So here's a max cut instance. Pretty obvious what the max cut is. This is what it is. Now, suppose I perturb the edge weights. And actually, here's how I want you to think about these perturbations, right? So first of all, suppose I made a pretty mild assumption about an optimization problem, that the optimal solution was unique. One different way of saying that assumption would be, if I make tiny perturbations to the objective function, the optimal solution doesn't change. Right? That's the same thing as uniqueness. So perturbation stability is just kind of uniqueness on steroids. It says not only does the optimal solution not change under small perturbations, it doesn't change even under somewhat big perturbations. So gamma here is going to be a constant, hopefully not too far from 1. And we're going to think about taking the weights of a max cut instance and multiplying each one by some number between 1 and gamma. Okay? So for example, let's think about gamma equal 2. So I want to say that no matter how I perturb these edge weights, multiplying each by their own factor between 1 and 2, I want the maximum cut to stay the same. Now actually, if you think about it, if there's going to be any perturbation which dislodges the optimal solution, it's kind of obvious which one it is, right? If I wanted to make it the least likely for the optimal to stay the same, I would not scale up any of the edges it's already cutting. And for the edges that it's not cutting, I would scale them up as much as I'm allowed by gamma. So if gamma equals 2, this is the worst perturbation, and the max cut stays the same. Okay? So that's the definition of perturbation stability. So it's for problems where you have either graphs and edge weights, or where you have a metric, so a distance function between points. And it says the optimal solution remains invariant as you perturb all of the input coefficients by factors between 1 and gamma. You can have a version with an epsilon, like with approximation stability, but let's just assume epsilon equals 0, and the optimal solution really stays the same.
So I don't understand the motivation really. Like the motivation that distance is often heuristics, in terms of that doesn't mean that the fact that motivation the distances may be heuristics doesn't really imply that the condition would be fulfilled, would it?
No, but you're hoping it would be fulfilled, right? So, thanks for the question. I meant to elaborate on this. So, like the Balkan et al. Result, what's being done here is taking a usually implicit assumption, when you're hoping your algorithm actually works in practice, and making it explicit, and then investigating theoretically, what does that imply about the instances. It's a different implicit assumption here than before. So here, they were motivated by, sort of distance measures. So like you have proteins and you have a notion of protein similarity, and then when you do some, say, like clustering or partitioning algorithm with respect to that distance function, you're really hoping that you don't get back an answer which is kind of an artifact of the details of your distance function. You're really hoping there's sort of a robust solution, like a robust clustering, which even if you had the distances a little bit wrong, you'd still get it back. Now, that's not going to be true in general, right? In general, misspecification does totally change what you get back. But they're saying, let's think about the sort of regime where you're implicitly assuming that it works. How do you write that down as a definition? What implications does that have for the complexity of the problem? Okay. So there's been nice work on max cut. I want to tell you actually a little bit about a different result, again, but about perturbation stability, which is the multi-way cut problem. So this is a nice result by Makarichev, and Vijayaraghavan. So in the multi-way cut problem, you're given an undirected graph, there are edge costs, and there are k terminals. Think of k as like 3, if you want. And then what you need to do is you need to partition the graph so that each of the terminals it's in is in its own group. And you want to minimize the cost of the cut edges. Actually, when k equals 2, you'll recognize this just as the normal ST min cut problem in a graph. So this is ST min cut, but with more than 2 terminals. Okay? So you can again define perturbation stable min multi-way cut problems. That just means that the optimal solution again stays the same under any of these perturbations. And one thing I meant to say over here is that notice that as we take gamma bigger and bigger, this condition gets stronger and stronger. The bigger the gamma, the more perturbations the optimal solution has to survive, so it's harder to do, so we're talking about fewer instances. So the complexity of this problem, it's going to be hard when gamma is 1, and as we jack up gamma, you might hope that it switches to polynomial time solvable at some point. So the question I want to ask for min multi-way cut is, what gamma is sufficient for the multi-way cut problem to flip from being NP hard to being polynomial time solvable? Okay? So that's a well-defined question. And the theorem I want to tell you a little bit about shows that gamma equal 4 is sufficient. So if you have a 4 perturbation stable min multi-way cut problem, that is the optimal solution is invariant over multiplying each edge cost by a factor between 1 and 4, then it is no longer an NP hard problem. It's actually a poly time solvable special case of min multi-way cut.
That's sufficient.
Sufficient. Yeah, so an open question is find the threshold for gamma. But this is the best positive result that we know. It's definitely possible you can still do it for smaller gamma. Okay, so I'm going to have to the proof is pretty cool, but I'm going to have to skip it. Questions are more important than proofs. So, but let me just say a couple words to sort of intrigue the experts, for those of you that know some of this stuff. So the way I like to teach this result is I first just review something about the ST minimum cut problem, which has been known for a long time, which is if you write down a suitable linear programming relaxation of the minimum cut problem, it actually just solves to integers. So even though in principle you might be worried about getting a fractional min cut back from your linear program, actually it hands you an integral minimum cut on a silver platter. Okay, so that's a property of the ST min cut problem. And this isn't like shocking because it's a polynomial time solvable problem, right? I mean, you could use max flow, say, if you wanted instead to find a min cut. You don't need to solve an LP. But actually the exact same argument of how you prove integrality of the ST min cut relaxation can be used to prove this MMV theorem. Okay? So again, the proof is going to be to show that a suitable linear programming relaxation is exact. It solves to integers. Okay? So that's the polynomial time algorithm. Again, here's where it's not tailored to the assumption. It's really just solve the LP, hope it works out, and you get an integral solution. Okay? And gamma equals 4 is sufficient for it to be true. And so you might be wondering about what is the suitable LP relaxation. It's a famous one of Kalinescu, Karloff, and Rabbani, where basically you embed each vertex into the simplex, and the LP pays according to 1/2 of the L1 norms. If you haven't seen it, don't worry about it, not important. If you have seen it, then this is to remind you. And then you can basically proceed as in the ST min cut case to show that it solves to integers if it's 4 stable. Where does the 4 come from? Well, so there's a nice lemma here where they use, and again, so it's going to be about a randomized rounding algorithm, but I want to emphasize, remember, this is going to be using a randomized rounding algorithm only in the analysis, right? The algorithm is just solve the linear program and hope you get integers. But in the proof, you actually use the existence of a randomized rounding algorithm with certain properties. Okay, it's an algorithm due to Kleinberg and Tardosh, originally from metric labeling. If you haven't seen it, don't worry about it. But basically, you lose 2 factors of 2 in different parts in the randomized rounding algorithm of Kleinberg and Tardosh, and that's what gets absorbed by the 4 in the perturbation stability condition. And once you have that idea, you literally write down just exactly the same proof you'd write for exactness of ST min cut, and that gives you the MMV theorem. Yeah, Kamesh.
It's 4 stable against the LP relaxation.
Yes, that's sort of what the proof does, yeah. Yep.
So you're solving the problems exactly. So the LP is the exact solution of the gamma perturb.
That's right. So feed in a 4 stable instance, and you will get back a 0-1 solution. And once you get back a 0-1 solution from an LP relaxation, you of course know you're optimal.
For example, in the case of machine, we always consider that the ones that we don't like to increase.
Yeah.
So is there any analysis in the case that, because if there is noise, it will affect all of them. So is there any analysis in the case that, like, not worse case?
Good question. I'm not aware of one, but you're right, it's a very natural question. The question was, could you imagine a definition where rather than opt being invariant to all perturbations in a certain range, you had invariant on average or in some weaker sense? I've never seen a result like that, but it would be nice to see one.
Is it known that the hardness result for the multi-way cut if gamma is 1.01 or something? I mean, if gamma is slightly larger than 1.
So no. Oh. No, we know nothing in between 1 and 4. And so let me use that to segue into kind of a very general problem, which I think is really interesting, right? So what has the algorithms community been obsessed over for 30 years? Approximation thresholds, right? You have an NP-hard problem, and for a sufficiently small, like for a 1 approximation, it's NP-hard. If you take the approximation ratio to be n or something big enough, it's almost always polytime solvable. And so you look for the threshold. Where does it switch from P to NP-hard? So that's a threshold you can attach to every optimization problem. Whenever you have these stability notions, not just perturbation stability, but also approximation stability, for example, you can do exactly the same thing. You can say, I have an NP-hard optimization problem in general. How strong do I need to make the stability assumption before recovery of an optimal solution becomes polytime solvable? Okay, so let me call that the stability threshold. So we have two thresholds for every optimization problem, an approximation threshold and a stability threshold. And I would really like to have some better understanding of the extent to which these two thresholds are related. The coolest result along these lines is actually the main result from the MMV paper, which shows that there is a very tight connection between these two concepts, but in different problems. Okay? The stability threshold for max cut, the original Biot lineal setting, corresponds to the approximation threshold for a different problem, sparsest cut. Basically because what's controlling both is low distortion embeddings from L2 squared to L1, if you know what those are. Okay? So that's very nice. There's a pretty tight connection between these two thresholds in different problems. If you look at the two thresholds in a common problem, it seems to depend. It seems like some problems approximation's bigger, some perturbation, the stability threshold's bigger, and sometimes they're the same. I'd love to understand what's going on a little more deeply here.
Just to understand that statement, so the threshold for max cut is like not constant, but it is some.
Yeah, square root log, you know, kind of thing.
So it depends on the graph size.
That's right. Yeah, depends on the graph size. Yeah. Okay, so last part for part one, and this will be quick. So I'm going to talk a little bit about sparse recovery. A huge topic. Obviously, I'll barely scratch the surface. So compressive sensing in particular. And what I'm sort of hoping is that at the moment it feels almost jarring to you that I'm going from, you know, clustering is hard only when it doesn't matter, to sparse recovery, you know, an area you've probably at least heard of, but associate with sort of different communities largely. And I'm putting these next to each other because I want to make it clear that the technical statements, the kinds of things you prove, is pretty much identical in these two lines of work. And there really should be more opportunities for technology transfer between the two areas. So let me just sort of review a famous result from sparse recovery to say exactly what I mean. So there's lots of sparse recovery problems, matrix completion, and so on. I'm going to look at compressive sensing. So this is the problem of trying to recover an unknown vector, it's called a signal in this context, from linear measurements. Okay, so basically you're going to be given an underdetermined linear system, and you want to figure out what is this unknown vector here. For example, maybe you're a geophysicist, you're looking for oil, and you want to know the structure of the rock strata beneath where you are. Okay, because oil is likely to be at discontinuities in the rock strata. So then what you're trying to learn, X is going to correspond to the structure of the rock beneath you. Okay? Now you'd love to just put a camera straight down into the ground really far and see what it is. You can't do that. So instead you send seismic waves into the ground. And just to be clear, sending seismic waves is a euphemism for blowing up a ton of dynamite. Okay? So that's what you do. You blow up a bunch of dynamite, and you see what kind of reflection do you get back of that seismic wave. Okay? So each of those seismic waves corresponds to a linear measurement or a dot product. So that corresponds to a row of A with the unknown signal, and then you get back the measurement, the amount of the reflection that you get. Okay? So again, to be clear, you know A, you even designed A. You don't know X, except in as much as you know the inner products of X with the rows of A, as summarized in B. Okay?
Sorry, one question. So how do you send the dynamite there when you cannot?
No, you blow it up at the ground, and then the waves go in.
But I mean, you need to send it deep such that you can see the deep stuff.
No.
It's out of. I see. So you can't.
Yeah. But isn't it just like, aren't you kind of thinking, I didn't know being a geophysicist could be so fun, right? Okay. So you know A, nature gives you back B, you want to know what X is. And notice that with no further assumptions, this is a totally stupid problem. This makes no sense, okay? Why? Well, at least in the regime I'm interested in where, as suggested, M, the number of rows, is much less than the number of columns. That would mean it's an underdetermined linear system. You don't have enough constraints to pin down all the degrees of freedom in X. So there's going to be a whole subspace of solutions to this linear system. I'm asking for the specific one X. How would you ever know which point in the subspace it is? It's crazy. It makes no sense. So how can we make it make sense? The key idea is to assume that the signal the vector is sparse. Okay, so it has, let's say, only k non-zeros, where k is much less than the length n. Okay, in practice, it's usually approximately sparse, but the theory extends to that. And also, maybe it's not sparse in the standard basis; it's sparse in some other basis, right? So maybe the rock strata are sort of sparse in the spatial basis because there's not too many discontinuities. An audio signal is going to be sparse in the Fourier basis. image is going to be mostly sparse in the wavelet basis, and so on. And the theory works for all of these. Okay? So that's the motivation behind the sparsity assumption. Most signals, or a lot of signals that one cares about, are sparse in a suitable orthonormal basis. And once you make that assumption, you say, well, okay, I have an idea. To recover X, again, remember, you know A, you were given B, you want to figure out X. So you look, of course, over the subspace of solutions to this linear system. And you say, well, if I know that the solution is sparse, let me just look for the sparsest one in the subspace. I'd have to get like pretty unlucky for this subspace to have two different super sparse vectors. So if I find a really sparse vector, probably that's the unknown X I'm looking for. Okay? Now, problem, it's NP hard in general to find the sparsest solution to a given set of linear equations. So we're going to look at a heuristic instead. And just like in multi-way cut, our heuristic is just going to be to solve a suitable linear programming relaxation and hope that it works. So what is the linear programming relaxation? It's called L1 minimization. So instead of minimizing the number of non-zeros, you minimize the L1 norm. Okay, so over all solutions to this set of linear equations, you find the solution with the minimum L1 norm. That can be written down as a linear program. You can solve it in polynomial time. Now, because this problem is NP hard, you know it's not always going to work. It's not. Okay, sometimes you'll get back something which is not sparse. It has non-zeros everywhere, and they're just all really small numbers, and that's why you had L1 norm. So are there any interesting cases where it does work under conditions on A, for example? All right? And this is exactly what we were doing in multi-way cut. Or you wrote down a linear programming relaxation. We know that in many cases it's going to solve the fractions, but is there some kind of imposition on the input which guarantees exact recovery? It's exactly the same thing you're after here in compressive sensing. And so there's a bunch of guarantees of this form for lots of different algorithms, but just to point out one. So under a condition on the constraint matrix A, then in fact, that's a sufficient condition for recovery. Okay, so I'll say more about this in a second, but under a condition on A, you solve the linear program, you get back actually the sparse signal that you wanted all along. Okay, so what is the restricted isometry property? The details aren't important. It says something like it approximately preserves the norm of all k-sparse vectors. It's also related to incoherence. That's saying that basically any pair of columns of your matrix are approximately orthogonal. Now, if you've never seen this before, you're like, is this a strong condition? Is this a weak condition? How should I feel about this? So one way you can sanity check it is you can say, well, what about a random matrix? And you start feeling better about this condition when you start realizing that kind of for most models of random matrices, you're actually going to satisfy this RIP condition with high probability. So in some sense, it's a much weaker assumption than assuming a random matrix. It's assuming just this deterministic condition, which is implied by random matrix models. Okay? All right, and again, I highlight this because it seems, there's a beautiful and deep theory around sparse recovery that's developed over the past 10 years. I think there should be opportunities to port more of those techniques over to the combinatorial types of problems that this crowd likes to think about. So that's an opportunity. So I'll leave the summary on the board, and I think we should break. Ganesh. We can talk about that. We can talk about that. There's a lot of really nice techniques in sparse recovery. So, yeah.
I think in both the last two results, the success was that it was solved by a linear program.
That's right.
But then earlier, of course, we discussed that linear programming as a polynomial time algorithm may not work well. So what is the guarantee that here?
What do you mean, sorry?
Well, before we said that some of the interior point methods, right? But it's not a good algorithm for practical problems, right?
Well, I guess the way I'm thinking of it is, if I look downstream, for whom would this theorem be sort of illuminating? I'm thinking about someone who bought a license to Simplex, or has installed an open source LP solver on their computer, and they want to have some understanding of whether it's likely to be sufficient for the problems that they care about, or whether they have to work harder or do something custom. And so this is saying, if you sort of believe that some kind of stability condition is holding for your instances, actually with your Simplex license, you're done. Okay? So I'm sort of thinking of linear programming for this part as a well-solved problem. Not only well-solved, but well-engineered and implemented and available for anyone to use.
There are some analysis that shows you are not in the cases where you becomes exponential?
Yeah, so that's a good question. So would there be any reason to believe that Simplex would be polynomial time anyways, also under the stability condition? No, I don't think anyone's thought about trying to connect these stability assumptions to running times. They've pretty much only been looked at to analyze sort of solution quality. Yeah.
You were asking about the threshold for perturbation resilience.
Yeah.
And Makarichev have a new paper on arXiv which says that you can get to perturbation resilience, and due to the Balkan et al. Paper, that's tight unless...
What problem are we talking about?
K median, K means, K center.
Cool. No, I mean, I highlighted one MMV paper, but they've done a lot of great work. They'll show up again in part 2 of the tutorial. This newest one I haven't seen, so thanks for letting me know. So. Okay. Yep.